All right. So again, we're going to be starting in on chapter 15, which is all about the kinetics of a reaction. So just to take a step back, in the last chapter, what we studied was thermodynamics, right? So that pertained to whether or not a reaction occurred. And looking at these reaction coordinate diagrams here, right? So these represent the progress of a chemical reaction in terms of the energy, starting at a certain energy for your reactants, right? And then ending at a certain energy for your products. And that we said that that was all that thermodynamics concerns itself with, right? We talked about how these thermodynamic functions were state functions. So they only really care where you start and where you end, not what happens in the middle. Okay, so that was last chapter. That was the study of thermodynamics, the delta G, the delta S, the delta H, all that business. Now we're going to talk about kinetics, which corresponds to the speed of a reaction. And if we look at our reaction coordinate diagram, the kinetics of the reaction are exactly what we said we're going to ignore for thermodynamics. What's happening in the middle here, right? So what path is taken from the reactants to the products? And more importantly, what we're going to be measuring is how quickly does this reaction go from reactants to products, right? That's what we mean by kinetics. And we want to have these two kind of separate in our mind, right? We approach them in very different ways. All right, so first of all, with kinetics, our main concern is the speed of a reaction. All right, and so we're going to talk about this in terms of reaction rates. We encounter rates on a daily basis in our lives. Most commonly with every time we step into a car, right? When we're talking about the speed of that car, we're talking about the rate that it travels. For our vehicles, we measure this in miles per hour, right? And that is the change in distance that's covered in a given period of time. Right? That's what your car is measuring when it's measuring your speed, is how much distance are you traveling in a given period of time. All right, and just to be clear what this delta means, right? The delta means change. So the triangle we say means change. Really what we would say is that delta T is the final minus the initial, right? The change in time. With regard to our reactions, we're not talking about a distance covered. Instead, for our reaction rates, what we're concerned with is changes in concentration that appear over a given period of time. So when we're talking about measuring the rate of a reaction, that's what we're measuring, is the change in concentration over a given unit of time. All right, and let's talk about how we get these rates here in a second. We can figure out the rate of a reaction by either measuring the amount of product that's consumed in a reaction, so the change in the product's concentration over time. Products increase in concentration throughout the course of a reaction. Or we can get the exact same value, the exact same rate, by measuring the change in the reactant concentration. But remember, reactants are consumed in a reaction. Their concentration decreases. And so if we're going to determine the rate of a reaction by looking at the change in concentration of the reactant, we're going to have to multiply it by -1, because we're going to make it that rates are always positive values. All right, so let's just make a note here. Reaction rates. They're always positive. Okay. Furthermore, let me just make some room for myself here. All right, they're always positive. And furthermore, they have to be the same no matter what you're watching in a chemical reaction. Meaning, if I'm measuring the amount of product produced, I better get the exact same rate as if I measure the amount of reactant consumed. Right, so same value. Regardless of what's being measured. All right, so every reaction will have its own unique rate. It'll sort of depend on the conditions as well as like how much reactant you start with. But if I have a given chemical reaction and I'm measuring its rate, it shouldn't matter whether I'm measuring the amount of product consumed, or rather product produced, or reactant consumed. I should get the same value for that reaction. All right, so let's take a look at a specific reaction here. We'll save this one. And we're going to convert this into our rates, right? Meaning we're going to build these rate expressions from this balanced chemical equation. All right, so importantly, I can watch the amount of hydrogen gas that's consumed in this reaction. But since it's a reactant, I'm going to have to multiply that by -1. Yeah, sorry. Usually I'm on top of that, but my computer's muted. Cool. Should be good. All right. So again, because I'm going to measure something on the reactant side, I have to multiply it by -1 because it's a reactant. Okay. Or I could measure the amount of product that's produced in the reaction. So the change in my HI concentration over the change in time. This is a product, so I'm not going to have to multiply it by -1. But importantly, I do have to account for this stoichiometric coefficient here, right? For every hydrogen molecule that's being consumed, I'm generating 2 of this HI here, right? And so in order to keep these rate values the same, regardless of what I'm measuring, I'm going to have to divide it by that stoichiometric coefficient, divide that concentration by that stoichiometric coefficient, so I get the same value every time. Okay. Now, what you would measure, I could measure either one of these and I should be able to get the same value, right? So it really depends on what's going to be the most convenient thing for you, given your particular reaction. For this reaction, just looking at it, actually, one of the more convenient things to measure would probably be the change in the concentration of iodine, because iodine is a brightly colored molecule. It's this bright purple molecule. So I could watch how that concentration changes over time by just watching the amount of purple that decreases. We sort of talked a little bit about these spectrophotometers in our transition metal chapter, which measures the amount of light that's being absorbed at a given wavelength. We could use that same instrument to watch this bright purple thing get consumed. Or we can take advantage of the fact that HI, hydroiodic acid, is a very acidic molecule. So we could take advantage of that to measure the concentration of that that's being produced. Again, it wouldn't matter which one of these things we viewed. We should be able to get the same reaction rate. Okay. And again, if it's a product, or rather, if it's a reactant, you have to multiply your expression by -1. Or if it has a stoichiometric coefficient, you have to make sure to divide by that stoichiometric coefficient so that all of your reaction rates are the same, regardless of what species you're watching in your chemical equation. All right, so everybody's going to take a minute and you're going to give me the rate expression for if we were monitoring hydrogen gas consumption or if we were monitoring ammonia production. Okay, so everybody take a minute and give me those rate expressions. No, we don't have to do it on iClicker because it's going to be kind of like this messy fraction thing here. So it's not going to be something that we can input very easily. So we'll save our iClicker to till we get to this next topic here. But right now you're going to build me an expression just like up here for the rate of this particular reaction if we were monitoring either the concentration of hydrogen gas or the concentration of ammonia that was produced. Okay, for my hydrogen gas, it's a reactant, so it's going to have that negative sign. And I'm going to have to divide by that stoichiometric coefficient of 3. So I would multiply the change in hydrogen concentration over the change in time by -1/3. All right. This would be equivalent to if I monitored the amount of product produced in the reaction. In that case, it would be 1/2, dealing with that stoichiometric coefficient, the change in concentration of ammonia over the change in time. Okay, so when we turn this into, we take our balanced chemical equation, we turn it into these rate expressions. Again, we're going to remember that reactants need that negative sign, and you have to divide by the stoichiometric coefficient, right? Because this value needs to be, this rate value needs to be the same regardless of what we measure in our chemical equation. All right. So what can we do with this type of information? So basically what you would do is you would conduct an experiment where you know, for example, let's use this one here. We mix together some hydrogen gas and some iodine, and we start the clock. And at various points in time, we record, you know, we could, again, monitor any one of these things, but we'll, for example, record the concentration of hydrogen gas as it's decreasing over time, right? Or we could record the concentration of the HI as it's increasing over time. And so what we would get if we took this data is we would get a plot that looks like this. Okay, so this is this reaction, the same reaction, hydrogen gas plus iodine yields hydroiodic acid. Okay, and so what we see here is that I monitored the change in hydroiodic acid concentration over time. That's that red curve that's increasing, as well as you can monitor the change in the hydrogen gas over time, and that's that green line that's decreasing. Okay, so before we sort of talk any more detail about this graph, let's just make sure that there are a few things that we can see here. So again, we can see that our concentration of reactant is decreasing. And that's because it's being consumed in the reaction. And we can see that our concentration of hydroiodic acid is increasing because it's being produced. Furthermore, we can see that for each of these changes that we see in our green line, for every sort of point that this green line decreases, so from here to here, we see twice as big of an increase in our red line. Right, so for every unit that we lost in our hydrogen gas concentration, we've increased twice as much in our HI concentration, right? And again, that's because of that stoichiometric coefficient. So increase in HI is 2 times the increase, or the decrease, so I guess -2, we can say, times that change in H2. Oh man, that was not gonna work. Sorry, let me clean this up. So our delta HI is twice as much and in the opposite direction as our change in hydrogen ion or hydrogen gas concentration. That's why we have to take, when we do our rate expressions, that's why we would have taken this one and divided it by 2 for monitoring the hydroiodic acid concentration. All right, so we do this experiment. We monitor the concentration of each of these two things as it's changing over time, and we get this plot. What is this doing for us? Well, so again, the rate, if we just want to look at one of these two, is 1/2 over the change in HI over the change in T. So the rate corresponds to the slope of this curve. Right? Rise over run. I don't know if you guys have heard that. That's what they taught us in math class. That's what your slope is. It's the rise, so the change in the y direction, divided by the run, the change in the x direction. And so we can measure the rate of this reaction at each point along this curve by sort of figuring out what the slope is. So measuring the change in concentration that occurs, right? So that would be this right here. This is how my concentration is changing over time. And then I can measure how time is changing over time, right? That's that difference in that x-axis right there, right? So for each point along this curve, I can go through and measure the slope of the curve at that point, and that would give me the rate of this reaction. All right, and I could do that by measuring either from the concentration that we of the hydroiodic acid, my product produced, just making sure to take that value that I get and multiplying it by 1/2, as we see here. Or I could do the exact same thing and just monitor the change in the hydrogen ion concentration. Oops. Over time. Okay. And so same idea. I would just calculate the slope by looking at the change that occurs in the y-axis. So this distance here versus the change that occurs on the x-axis. Right. So we can measure the slope of this line, of this curve at each point, and that would give us the rate of the reaction. All right. And so what we can see, because this isn't a straight line, this is indeed a curve. If we look, for example, at this red line in particular, we can see that the rate is changing as this reaction proceeds, as it approaches equilibrium. When we start off our reaction, it's going at its fastest at the very beginning, right? That initial rate is going to be the largest value that we calculate because that's where the slope of this line is the steepest. As the reaction proceeds, our slope, right, it goes from being pretty vertical to starting to decrease, decrease, decrease. So towards the end of my reaction is where the rate is the slowest. Okay, so the last thing that we should be able to see based on this, this curve here is that the rate decreases over time. Right? The rate of this reaction is decreasing, it's slowing down as it approaches that equilibrium. And this is something that's going to be pretty common to see. Most reactions get slower as they occur. Not all of them, we'll see some exceptions, but they will all start out with their fastest, their steepest slope, their fastest rate being at the very beginning of the reaction, right? So the initial rate is always the largest. Okay. All right. So now we can see how we take these plots, right? So this would be the sort of data we would collect in the lab. We would create these plots. We would analyze the slope, and these would give us the rates of these reactions. Okay, so what can we do with this information? So we're going to kind of build up to something here. We're going to need to learn some skills, some ways to analyze this data and to get certain information. And then after we sort of learn how to do that, then we'll bring it back to what we can learn from our reactions from that information. Okay. So now we're going to graduate to talking about rate orders for a reaction. As we said that or as we actually just saw visually, the reaction rate changes throughout the course of the reaction, right? So rate of reaction changes over time. And really, it's because it's not just that it's changing because the time is increasing, right? Reactions don't know what time it is. The reason why your reaction rate is changing is because the rate of the reaction depends on how much reactant you actually have in there, right? So the rate is dependent on reactant concentration. All right, so we're going to take a look at a very simple type of reaction in order to help define our reaction rates, our reaction orders. And then we'll sort of graduate to more complicated reactions. So the first thing we're going to look at is just a simple unimolecular reaction where you have one reactant being converted to product. All right, so an example would be one that we ended with last class, actually, the decomposition of this dinitrogen tetraoxide. This would be an example of a unimolecular reaction. You only have this one reactant decomposing into the products. Okay. For these types of reactions, we can simplify our rate expression in terms of its dependence on the concentration of reactant as the following. The rate equals little k, so not an uppercase K like we do for equilibriums, but a lowercase k. Try to dramatize that. Times the concentration of that reactant to the power of n. All right, this is our rate expression for the concentration of our reactant. So let's pick this apart real quick. The rate is, of course, what we're measuring in our reaction. K is what's called the rate constant. All right, so similar to equilibrium constants, it's something that's going to depend on your particular reaction. Each reaction will have its own unique rate constant. If we know the rate constant, then we can actually predict the rate of the reaction at various concentrations, right? At various starting points. The concentration of A is, again, just the concentration of reactant. And then in this rate expression, you raise the concentration of the reactant to the power of n. This is what's called your rate order. All right, and this isn't necessarily something that you would just know as the equation for a rate. This is something that has been experimentally determined over time, that reactions fit very nicely into this type of rate expression here. And the vast majority of reactions will work out nicely in this respect, where the rate order is either 0, 1, or 2. All right, so for a given chemical reaction, we don't know this just by looking at it, but we can go in and measure the rates, and specifically the dependence on the rate or the dependence on the concentration of reactant for the rate. And then we can figure out this rate order, and it turns out that the vast majority of reactions will fit nicely into this type of equation, where that rate order is either 0, 1, or 2. Okay, you don't know just by looking at a reaction. You have to go through and actually analyze the data to figure it out. But these are by far the most common values for n. There are other reactions that are possible, other rate orders that are possible, including numbers greater than 2, as well as fractions, but they're super rare and not what we're going to be focusing on in this class. So our reactions that we look at will always have a rate order of 0, 1, or 2. Okay, and our goal is to figure that out. All right, so given a set of data, we want to be able to determine whether or not we have a what's called a 0. So if n equals 0, that's a 0 order reaction. If n equals 1, that's what we call a first order reaction. And if n equals 2, that's what we call a second order reaction. All right, and the reaction order does tell you some interesting information about the reaction itself, but we're going to have to lay some groundwork and learn a few things before we can really convert that information into something useful about what's going down in this reaction. So for right now, all we have sort of learned is that our rate of our reaction is going to depend on the concentration of the reactant. And it's going to depend specifically in this sort of fashion right here, where you take that concentration of A and raise it to the power of either 0, 1, or 2, depending on your specific reaction, right? We don't know what it's going to be until we look at the data. All right, so let's take a look at some data here. Here is, so first of all, how are we going to determine reaction rate? Let's take a step back, actually. Determine reaction rate. All right, we need to be able to do this one of two ways. The first way is called the method of initial rates. And the second is a graphical analysis method. All right, the graphical analysis is actually a little bit easier to do as long as you have all the data, right? So in order to do this graphical analysis, we need lots of data. Method of initial rates is good when we have a limited amount of data. Okay. Cool. So let's focus on this method of initial rates here. Okay. So first of all, if we take a look at our different reactions, so again, we said n equals 0. That's a 0 order reaction. If we take our equation and we take that n and raise it to the power of, take that n and replace it with 0. So we're taking that concentration and raising it to the power of 0. What's going to, I guess we can, let's make this an iClicker for the sake of getting our attendance in. All right. What is this equation going to simplify to when I take my equation and I replace n with 0? Right, so anything to the power of 0 is just 1. So I have k times 1. And so my rate expression will simplify to the rate equals just k. Right, so for these 0 order reactions, what's going to characterize a 0 order reaction is that it's independent of your reactant concentration. All right, most reactions will depend on, many reactions, let's say, will depend on the concentration of the reactant, unless it's a 0 order reaction, which is independent of the value of A. So we can see, if we look at our example here, this is not a 0 order reaction because our rate was changing over time. Right? If not, it would have been a constant slope. This one was changing, so we don't really know what this reaction is yet, but we can say that it's not a 0 order reaction. But again, we want to learn, or we want to know how to do it based on, again, this, what's called the method of initial rates. So what this is we're going to take our reaction and we're going to measure these first little bit here, this initial part where it's the steepest, and we're going to do that at a few different concentrations. Okay, so our data that we would get would be something like this. Okay, so the method of initial rates. We're going to measure the rate of the reaction let's say in the first few So that's kind of a sloppy way of saying it. You're going to measure the initial rate of the reaction. Depending on the reaction, if the reaction's really slow, you might need to measure it for a few minutes. If it's really fast, you might need to measure it for a few seconds, right? But you're going to just measure the initial rate of that reaction right after you start the clock. Again, exactly how long you measure it for depends on the reaction itself. The important bit is you need to measure it for the same time period for every single one. So we're going to measure the initial rate of the reaction for the first few time periods, and then we're going to change the concentration of your reactant and repeat it. Repeat the experiment. So what you're going to get at the end is for various initial concentrations of your reactant, you have the initial rate of the reaction. Right, so I'm going to start the clock. I'm going to measure my reaction rate at the very first beginning where it's its fastest. And then I'm going to change my concentration of reactant, and I'm going to repeat this process over again. Right, and so then I would get a set of data that looks like this, where I have my concentration of A and my rates at those various points. So then the method of the initial rates is we're going to take two of these and compare them. All right, and what we're going to do is we're going to take advantage. So the rate is equal to K times the concentration to the power of N. This is what we're trying to find in this reaction, or in this analysis. So what we're going to do is take the rate of one point and divide it by the rate of another point. Okay, take the ratio of those two. And actually, it really doesn't matter, but I am going to flip this because it's going to make the math easier for us to do in our head here. So I'm going to take my second point here. So we're going to call this point 1 and this point 2. And I'm going to take the rate of the second point and divide it by the rate of the first point. Using my equation, that means that I'm taking K times the concentration of A at that first point to the power of N, and then taking K times the concentration of A on that second point and raising it to the power of N. All right, all I did was plug in my equation there, just like I had here. Now, because this rate constant is constant, just like the name implies, this will actually cancel out of this here, which is why this is going to be very useful. You don't actually have to know the rate in order to determine the order of the reaction. I'm sorry, you don't have to know the rate constant in order to determine the order of the reaction. So now we're going to plug in our variables, right? So the rate at point 2 was 0.015. The rate at point 1 was also 0.015. My concentration at point 2 was 0.4 to the power of N. My concentration at point 1 was 0.20 to the power of N. Importantly, because of how exponents work, this would be the same as 0.40 over 0.20 to the power of N. Right, so I can do that division before I raise to the power of N here. Okay. So now if we sort of plug in our numbers or enter our numbers into our calculators, we get 1 equals 2 to the power of n. Okay. So what is n going to have to be in order to make this equation true? How do I solve for that? Right. So let's see. In terms of our iClicker, if anybody can see what the value of n has to be in order to make this statement true. And it's always going to be one of 3 options, right? 0, 1, or 2. So which one is going to marry this expression here so that this is actually true? Awesome, yeah. So we can see that n has to be equal to 0. So let's just sort of convince ourselves of this algebraically, sort of do it the long way here, because I think that you can kind of see that it should be n, but it's going to be harder if it's not a 0 order reaction. So how could I tell? In terms of our algebra, what we're going to have to do is take the log of both sides. Right? So I'm going to take both sides and I'm going to hit it with that log function. We can do anything we want to an equation as long as we do it to both sides. So I get the log of 1 equals the log of 2 to the n. And because of how logarithms work, this would be the same thing as n times the log of 2. Okay. Like this isn't an algebra class. Hopefully this is something that you would know about logarithms from your algebra class. If not, you're just going to trust me on it, right? By taking the log of something to the power of n, this is equivalent by multiplying n to that expression. So this allows us to pull that n out more or less. So then I have the log of 1 equals n times the log of 2. And I need more room. Crunch all this up. All right, so then this means that n is just equal to the log of 1 divided by the log of 2. The log of 1 is 0. So 1, it doesn't even matter what the log of 2 is. 0 divided by anything is just 0. Right? So that's how I can determine the rate of this, rather the rate order of this using this data. Right? And again, the trick is to take the ratio of 2 of those data points. All right, so now you're going to tell me, and so to be clear, yes, this was a 0 order reaction. All right, so now you're going to take this data and do the same thing. Right, again, we'll call this point, it really wouldn't matter which 2 points you chose. You can convince yourself of that. You could actually choose this one and this one if you wanted to, right? For the sake of simplicity, we're going to say that this is point 1 and this is point 2. And you're going to figure out what n is using the fact that the rate of the second point divided by the rate of the first point is equal to k times the concentration at the first point to the power of n over k times the concentration of this. Oh, whoops. Sorry. Point 2 should be on top and point 1 on the bottom to the power of n. All right. And we're going to do this as an iClicker. When you get done, you're going to tell me if it's a 0 order reaction, a first order reaction, or a second order reaction with your iClicker here. Okay, so everybody take a minute and solve for this rate order given this rate of initial the method of initial rates. Right, and again, our K is going to cancel out. Oh, crap. I meant to make it a multiple choice question. Sorry. ABC, what's it going to be? All right, so first of all, I know this is not a zero order reaction before I do any math. Okay, look at the data for the zero order reaction. What was a characteristic of that zero order reaction was that the rate did not depend on the concentration, right? The rate wasn't changing for every one of my data points. That's a zero order reaction, really easy to spot. And we showed it the long way, but again, it was sort of easy to spot. And this data here, my rate does depend on my concentration. So it's definitely not going to be a zero order reaction. Okay, I'm just going to plug in what I get for my values. So the rate of the second data point is the 0.060 divided by the rate of my first data point, the 0.15. This is equal to the concentration at the second data point, that 0.20 to the power of n, divided by the 0.10 to the power of n, which is, again, we can simplify that ratio to the power of n. Okay, so then we're going to plug it in. So this ratio here would be 4. Can be good with my sig figs. 4.0 is equal to 0.1 divided by 0.2 is 2.0 to the power of n. So again, you can, there's only going to be 3 answers, right? So you could figure this out by plugging in 0, 1, and 2 for n in order to figure out what it would be. Or if we're going to be really skilled with our algebra, we can take the log of both sides. And again, this is probably the trickiest bit here, is knowing your logarithm algebra, how this is equivalent to n times the log of 2. All right. And so then we can rearrange. We take the log of 4 divided by the log of 2. That's equal to n. If you punch that into your calculator, you would see that n is indeed 2. So this is a second order reaction here. All right, so that is this method of initial rates for determining your reaction order. Again, when we learn a little bit more, we'll be able to take this reaction order and use it to say something interesting about the chemical reaction itself. We got to lay some groundwork first.